The front side of the notes today only talks about two things, and actually one of those things is literally just a single line. It's right here. And so what it's saying here is the reason that log base 3 of 3 is 1 is because 3 to the power of 1 is equal to 3. So that means that log of any base, so even 7, I mean just make up a random number, of itself or of that number is always going to be equal to 1, because remember how I mentioned you need to learn to read these logs as questions. This log right here is saying 7 to what power is 7? So it's 1. And that's true always. I mean, if I did log of 10, remember that the invisible base on that common log is a 10. So whether or not the base is there, you are being asked 10 to what power is 10. So anytime you have the same number for the base as inside the log, it's always 1. Okay? That's the only mention of that on the front side. The rest of the front of these notes talk about how logs and inverses, or logs and exponentials are inverses of each other. And up here it's talking about how they cancel each other out when you plug them into each other. So just a couple of reminders. I'm going to jump around a little bit. Remember that if two functions are inverses of each other, that they are reflections of each other over the line y equals x. What that does is it takes the points on the graph and it switches the x and y. So here's e to the x. If you plug a 0 into that equation, so e to the 0, the answer you get is 1. So that's why the point 0, 1 is on that graph. Well, here's its inverse. Y equals natural log of x. And that point will switch the x and y coordinates, and so the point 1, 0 is on that graph. And that is because natural log of 1 is equal to 0. So remember that inverses switch the x and y coordinates. Remember that they counteract each other or cancel each other out only when they're touching, though. And we'll talk more about that in class over the next couple of days. And what that means, though, is here on problem 3, there's two different scenarios. One, this top row, says you've got a log, in this case with a base of 2, and inside of that log is an exponential with a base of 2. And so because they're in direct contact with each other, they're touching, the log with the base of 2 will cancel the base of the exponential that's 2, and the only thing that would be left is your answer, which is the 5. The second row is the alternate scenario. Instead of having a log and inside of the log an exponential, now we've got an exponential, and in the exponent is a log. But that exponential with a base of 2 is still in direct contact or touching the log with a base of 2, so they would still cancel, and your answer would still be 5. So take just a quick split second and tell me what that means the answers to the other ones would be. Okay, you don't even need to pause it. Okay, so hopefully you caught on really quick to that. Remember that this common log has an invisible base of 10, so this log will cancel this exponential space, and your answer would have been 6.2. Here, remember the invisible base for a natural log is e, so natural log with a base of e will cancel the base of the exponential with e, and your answer is x plus 1. And then here, this exponential with a base of 10 will cancel this common log with a base of 10, and your answer is 100. And here, an exponential with a base of e will cancel that log with a base of e, that natural log, and your answer is x minus 5. Okay, so it is just that straightforward. So what that means down here for this very last problem is that the natural log and the e will cancel each other out, and your answer is the square root of pi. So no matter how messy or ugly the numbers, if your inverses are touching, they will cancel each other out. The back of the notes is where we need to concentrate. So the one thing I'm going to do, I don't know how many people have been taught this. The 3 primary laws of logs are actually the same as the 3 primary laws of exponents. They just look very, very different, obviously. So the first primary law of exponents says that when you multiply two things that have the same base, their exponents add. And that's what this first law says. What we've got is we've got this product, it's xy, and it's inside of a log, which means we're trying to find its exponent. Because remember, that's what logs do, is find exponents for things. So what this property says is that it's going to find the exponent for the x, that's what that first log does. It's going to find the exponent for the y, and then it's going to take those two exponents and add them. So I understand that it's a lot messier, it's a lot more abstract, but it is the actual same law as the law of exponents, so just keep in mind, okay, always say this to yourself, multiplication results in addition. That means by default, though, the second law, that when you divide two things that have the same base, their exponents will subtract. So that's what this second law of log says. Here we've got a quotient of two things. That quotient is inside of a log, so we are attempting to find the exponent for that quotient. And so what this law says is it says find the exponent for the top, find the exponent for the bottom, and then take those two exponents and subtract them. So I understand that it's a completely different form, and you may not understand the log form of that law, but just recite to yourself that division results in subtraction. And then the final of the three primary laws says that when you have something that's being raised to a power and you raise it to another power, that the two powers multiply together. And that is what this law also says. So this log is trying to find the exponent for this thing. But that thing already has an exponent attached to it inside. So what happens is that inner exponent moves down to the front right here. So now the inner exponent is multiplying to the other exponent. And so raising to a power results in multiplication. Okay? Now the way that we use these is to do three things. The first thing we do is we expand logs. Now normally you would want to try and expand a log really only if you were going to try to rearrange it and evaluate some parts of it. We really can't do that with these practice problems. We're just trying to practice these laws. So for example on 16, the only thing we can do is that these two things right here are being multiplied together. And remember, multiplication results in addition. So that means that when these two things get split up, the 5 will get its own log with a base of a, and the x will get its own log with a base of a, and those two logs would add. Okay, so I want you to pause, and I want you to attempt 17 through 20. Okay. Okay, so hopefully you paused and you took a minute and you did 17 through 20. So on 17, the only thing you would do is move this 5 down to the front, and so your answer would have been 5 times the log of x. On 18, you actually have 3 different answers that are all correct and equivalent. Most people would just do log base 3 of 15 minus log base 3 of 7. And they would stop there. And that's okay because you weren't told to do any more. But 15 is also a product. 15 is 3 times 5. So you could split that up some more. You could say log base 3 of 3 plus log base 3 of 5 minus log base 3 of 7. And then you could even take it a step further, because log base 3 of 3 is, hopefully you're secretly thinking to yourself that it's equal to 1. Remember, the question that it's asking you is 3 to what power is 3? So it's equal to 1. So you may recall in Algebra 2 that there were at least one homework assignment, and then of course there were some questions on the test where you would have been given this as a decimal and this as a decimal, and then you would be given like a whole section of problems that said, now evaluate all these other logs in terms of these two decimals. If that was the case, you would need to take this as far as you could. You would turn this into a 1, and you would plug decimals in for this and this. We weren't told we had to do that. We weren't given those decimal values, so all three of these are correct and equivalent forms. It's just a matter of how far were you able to take it. And then on 19 and 20, the only thing you would need to do, they both work out the same way, is you need to rewrite what's inside the log. The cubed root of y is y to the 1/3. And so now that 1/3 is written as a power, so now it can move down to the front and become multiplication. So 1/3 times the log of y. And then the same thing goes for number 20. You would rewrite that 125 as 5 cubed. So now it's written as a power, so that power can move down to the front, and it would be 3 times log of 5. Okay, so this is what we call expanding the log. So whenever we ask you for expanded form, that's what you would do. Okay, when we go in the opposite direction, we're going from expanded form into condensed or compressed form, then what you're going to do is use those laws in reverse. So number 21, all three of those logs have the same base, so they're able to combine. These first two logs right here are separated by addition, so when we put them back into a single log, the two things inside of them would multiply. And then this final log is separated by subtraction, so when it goes back inside the log with the others, it wouldn't multiply, it would divide. And that is your compressed or condensed answer. Number 22, you would follow PEMDAS, and so these two would combine first. So the log base 2 of 5 is not changing at all for right now. These two are separated by addition, so I'm going to put them back inside of a single log, so log base 2 of, and then I multiply those two numbers together and they multiply to make 36. Now I can consolidate these two logs, and they're separated by subtraction, so they'll combine using division instead, and so that means the 5 is going to get divided by the 36. Okay, now one thing that I did in class that I want to try to do here, it's obviously harder to do all this kinds of stuff with a video, but on 23 I'm going to write the answer incorrectly because I'm hoping that you will catch the same mistake that your classmates did. These two logs are separated by addition, so I need to put them back together with multiplication. But one of the biggest mistakes people make is they write the answer this way. They take this and they multiply it times this, and actually fortunately a lot of them do remember to FOIL, but then they write the answer like this. So I want to see if you guys can figure out what's wrong with it like your classmates had to. Okay, so I'm hoping that you're looking at it and you realize that something's wrong. You may realize that this and this were inside of parentheses for a reason. Because of the addition or subtraction, the only thing technically inside the log right now is the x squared. If I need the x squared minus 9 to be inside the log, the x squared minus 9 needs to be in parentheses. Okay, it's a lot like your sigma notation. So just make sure you're really careful about that. It's a common error, happens on multiple types of problems. So anytime there's addition or subtraction, you need to make sure that it's in parentheses. And then on 24, we can't combine these two logs because of the addition yet, because they both have coefficients in front of them. But the only place a coefficient in front of it could have come from is up at the exponent where it would have originally started out. So the first step is to move those numbers back up to the exponents where they were. So the 2 will move back up to be above the 8, and the 1/3 would move back up to be above the 27. And so at that point what we would have is 8 squared is 64, and 27 to the 1/3 is the cubed root, so that would be 3. And now I can put them back together into a single log, so log base 5 of, and then the two numbers would multiply and we would get 192. Okay, and that is as compressed as it gets. Okay, last but not least, remember, of course, that the base of your log needs to be bigger than 0 and it can't be equal to 1. We're not going to use this property until tomorrow, so hopefully that helps at least a little bit. And so the property we're going to use to do these last 4 problems is A. And it also has an exponent form. The exponent form says this. It says if x to the power of A is equal to x to the power of B, then we know that A is equal to B. Okay, it's what we've called dropping the bases. So we've been able to set these exponents equal to each other. The same is true of logs. If we have a log equal to a log, their bases are the same, then we get to drop the logs and bases because we know that whatever's inside of those logs must be equal. Okay, so what that means is that you've got to have a single log on each side of the equation. So on 25, the left side is already good to go. It's already got a single log. Okay, but the right side we need to compress or condense. And so I'm going to put these into a single log. These two are separated by addition, so I'm going to put their numbers together with multiplication. And then this log is separated by subtraction, so its number is going to get divided. And so we would have log base 3 of x on the left side, and we would have log base 3 of 10 on the right side. And that means that we can now drop the logs and bases, and x is equal to 10. Okay, so I want you to try 26 and 27. I want you to pause. If you can, work 28. If you remember how to do it, it is different than the others, so we'll see how far you can take it. Otherwise, we will work it together before we're done. Okay, so hopefully on 26, you got x was equal to 100, and all you did was move that 2 back up to the exponent where it came from. On 27, you move both coefficients back up to the exponent where they came from, and then you drop the logs, and you have x squared is equal to 4. And hopefully you remember that when you square root to solve, you always at least initially consider both the positive and the negative answer. Now here's the thing about this particular problem. There are times the negative number will work, depending on the format of the log. And I'm going to I've talked to your classmates about it today. I'm going to write an example of when a negative number would work. Okay, but in this particular case, this negative number won't work. Because if a negative number is going to work inside of a log, then it can't just work in the original log equation. The laws of logs would have to work in all possible arrangements of that equation. So in this original version of the equation, the negative number would work because the only place it would get plugged in is right there as x to the 4th, and raising it to the power 4 would make it become a positive number. So that's not your problem. Your problem is that if it truly is a number that would work, then that means the laws of logs should allow this 4 to freely move down to the front. Well, if that 4 does move down to the front, then this x is here by itself. And plugging the negative 2 now means that we've got a negative number inside that log, so it won't actually work with all the different ways that equation could be rearranged. So you have to throw it out, and your answer is only x equals positive 2. Now, as I warned your classmates, that's not always the case. If we had gotten these 2 answers, but let's say we had gotten those 2 answers from an equation that looked like this instead, then in this case, that 2 right here is not free to move down to the front. It's stuck inside of a quadratic, inside of parentheses, inside of the log. So plugging a negative number into an equation like that would be okay, because negative 2 squared would be 4 minus 1 would be a positive number inside of that log, and there would be no possible ways to rearrange it so that the negative number wouldn't work. So don't just think that the negative numbers get thrown out. Now, most of the time, they do. You can't plug negative numbers into logs. But there are times where once you have plugged a number into a log, it doesn't stay negative. And then it would be okay. And then the final problem, I'm going to have to erase to make some room. Okay. The final problem is different because there's no log on the right side. So I'm going to go ahead and the first step is the same. I need to consolidate the left side. So I go ahead and I combine the left side. I'm going to have log base 3. Make sure you remember parentheses. It's going to become x squared plus 8x. And it's equal to 2. Okay. I don't have a log on the right. So I have two options. Option 1, I'm going to put a log on the right. So I leave the left side, log base 3 of x squared plus 8x. And I attach a log to the right side with the same base, but that doesn't change the size of the right side. Log base 3 of 3 is 1. So I just attached a 1 to that 2. But what that does is it puts a log on the right side. So now this 2 can move up to the power where it would go. So the left side stays the way it is. And now the right side becomes log base 3 of 3 squared, which is 9. Now I do have a log equal to a log, and I can drop the logs and bases. Okay? And the reason I'm not going to finish that problem quite yet is because the other method I have will take me to the same place. Okay, so the other method that I have is, it works better if I had just gone over the homework with you, but you weren't in class today. So remember that one of the homework problems you guys had to do said that log base 2 of 8 was equal to 3, and on the homework you were asked to convert it to exponential form. So it was this base to this power, so 2 cubed is equal to whatever was inside the log, which was 8. That's the same notion as this. So we're going to take this base, which is 3, to this power, which is 2, and it's going to be equal to whatever's inside the log, x squared plus 8x. So any way you cut it, whether you did this method or this method, you end up at a place where you have 9 is equal to x squared plus 8x. From that point, the rest of the process is the same. It's now a quadratic, which means you need to get it set equal to 0 so you can factor it. So I set it equal to 0 by moving the 9 over, by subtracting it. It factors as x plus 9 and x minus 1. And so I initially get two answers, x equals negative 9, x equals positive 1. But here's my original equation, and if I plugged this negative number into that equation, I'd have negatives inside of both of my logs. So it gets thrown out as extraneous, and x equals 1 is the only one you keep. Okay? Today was the only really long day of notes in this entire unit. Tomorrow will be much shorter, and then next week when we finally hit the pre-cal level of stuff, most of it's actually broken up as warm-ups and little things like that, so 10-15 minutes here and there throughout next week. So feel free to ask questions, feel free to work in class, feel free to come to tutoring, and be ready for Monday's quiz. Thanks, I'll see you guys later.